As you heard, I'm from Framatome. I've been working at Framatome for some years, particular on aging management for electrical and INC components. And in the frame of the aging management, was in charge of particular equipment qualification projects dealing with components you found in the electrical systems in a nuclear power plant, by drives, sensors, and in all electrical systems you also find cables. And today I want to talk about the significance about cables in nuclear power plants. Before, I will try to give you a picture from the bird's eye view of or on this field of work to understand why do we need software, which will be the main topic of my presentation. I will present you some features from COMSY, but I want to go one step back to show you why do we need software. So, and here we see the starting point in general is the region law. Although I think we have no Americans here. For example, I chose American law to show you, because the other ones maybe you know, but it's quite similar. In all cases, it's the same. You have to assure safe shutdown of the reactor. By certain systems, you have to keep the pressure boundaries by your safety systems. And you have to assure that the radiation keeps inside the reactor building. On top, you have to deal with systems which are not directly connected to safety systems, but whose failure may impact safety systems. Mostly, it's just a subject of installation stability. But in the frame of aging management, it also is possible that operational systems are systems which are not designated as safety related from the beginning of the plant. When the plant built up, the design decide what is safety, what is not. But over the time, also the law changed, the experience were gained, and therefore the plants are forced to re-evaluate its safety philosophy. And this may lead to the fact that also operational systems become safety-related ones. So this is a big challenge here. And a problem of the power plant, and we heard this in other presentations, is that we have to deal with a huge number of cables. Each electrical system consists of cables, and we have to deal with about 40,000 cables per unit. And this is the most relevant reason why we need software to deal with that. Because the operators need to demonstrate the safety of the plant, and that means they have to demonstrate that each cable in each safety system is in a good mode. Yeah, although in plants a single failure is acceptable, it is not acceptable to operate in a run to failure philosophy. This is not acceptable, and therefore you need to perform some evaluations, and you need predictions. So, and here we'll give you the significance or the meaning of the cables in a containment application. So I'm not sure if we use the term function chain. It's a special thing of German plants. That means that it is not enough to have an equipment qualification for each single part used here. It is the main question is the complete system able to withstand higher environmental conditions, for example, in the frame of an accident, or will we lose the component, the function of the component? So, and one important property of a cable is that the insulation resistance, which is 50% of the intended safety function of a cable, increase or decrease with the increase of temperature and pressure. And temperature and pressure are common loads in nuclear power plants. Therefore, we have to be careful with that. So, and now what is the reason why maybe we lose the function of this drive, which maybe work to close an important valve? If you have lower insulation resistances here on the cable runs, you have electrical load in parallel to the motor here. In this case, that means the main current will increase, but you have a motor protection relay, and this motor protection relay is adjusted to the rated current of the motor. But if the current increase, you will lose the function because the safety protection relay will switch off. In a case of the INC, it's quite similar. You have our insulation resistances, and these ones are in parallel to the input resistance of the amplifier. That means the more the insulation resistance come down to the input resistance of your electronics, the higher the relative error of the measurement, and you have requirements, for example, 5%, no more. And this is a task of the operator to assure that the failure in a case of an loss of coolant accident will kept in the range which are acceptable. And the second intended safety function of a cable, according to American guidelines, is the transmission of current. But this is not really a subject to aging. Here we talk about metal, and our experiences show that is not subject to aging. So we have the focus on the core insulation of the cables. So here some examples. This is a qualification test I performed, I think, 10 years ago. Here we see the insulation resistance of the cable in the course of a local simulation. So that means we put the cable into a pressure chamber, applied pressure and humidity 100%. And what we see here is when the temperature and the pressure increase, the insulation resistance fall. And we see here we are in the mega ohm area, which can be maybe a problem for sensitive INC measurements. So, and after the simulation, when the temperature is decreasing and the pressure is going lost, the insulation resistance climbed to the initial behavior of the cable. And this is what we have to treat, and we have to demonstrate that our plant is in a safe mode, although it can be exposed to a local accident. This year is, for example, a electrical circuit doing local simulation tests. One core is measured between all others, and then it switched according a certain pattern. So each was measured against all others, and then depends on the course, you have a certain number of patterns. Doing this test here, we found some degradations, very important, because we found a cracking of the sheet. It's not function relevant because we have the focus on the insulation, and as the picture here shows, this cable withstand the test, but we have mentionable degradation at the sheet because of the pressure and depressure phase. This was the reason for the crack. Here, some other examples we have to deal with. This is a terminal box of the motor after a local simulation for long term. That means 1 year of local and the post-local phase was simulated within maybe 2 or 3 months in a kind of climber and corrosion test. And as you see here, these are manageable loads the equipment is exposed to. Here, some internals of a cabinet. Here we see some crackings, not really relevant, but it is not what you want to find in a nuclear power plant here for the sheath. Okay, so for cables, and now I come close to COMSY software. We have to determine the relevant data, such like environmental data the cables are exposed to, because this is the reason for the aging, as we know. And in case of electric cables, we have to check if if the motor, mostly a motor is at the end, is operated continuously or not. If not, you have no self-heating of the cable, no manageable, only for maintenance activities. Not significant, but you also have permanent operated big or huge motors, and you will find manageable self-heating, and you need models or calculation methods to determine the temperature at the core, because it is easy to measure the surface of the cable, but this is not representative for the core temperature of interest. So, and there are formulas. I didn't copy it because we didn't develop. You find it in any books. You need some parameter like energy, heat transfer coefficient, thermal conductivity, and your environmental temperature. But these values you can calculate the core temperature, and this temperature is important when you, as Karel yesterday also showed, when you calculate your residual lifetime of the cable, you do it in connection with the environmental temperature, and you have to add the self-heating on top. And this is the representative temperature you use for your, for example, Arrhenius model. Mostly we work with Arrhenius model to calculate the residual lifetime. So here we see one window from COMSY. I avoid to show you software presentation. I am not friend of that. To show you what happened when I click here or there. I will try to talk about the main features here. And one important thing here is, and this is exists to the right to exist for the COMSY. COMSY is applied in several plants and is able to build up the plant graphical because of the data input consists of all electrical equipment. In this case, I reduce it to electrical. No? We have the function chains. You remember the picture 2 slides before. The function chains are entered. All cables of the plant we imported from the plant certain operation system in COMSY, and we can treat this data here. And the big advantage for the topic of the day here is that we do not need to do this twice. So if we have a virtual polymer adaptation, we have an interface, we have access to the algorithm you developed, and we can use the existing plant information. And by this, we are able to treat 40,000 cables. The prerequisite is for sure that these cables are already entered, and the environmental conditions, the material conditions, our device library. This is a library giving material-specific data like activation, energy, and so on.
5 minutes.
5 minutes, okay. Okay, I will hurry up. Okay, so the thermal degradation assessment consists of the application of the Arrhenius law. This is the best we have at the moment, which is applicable. There are a lot of models, much better, but you need more information of the certain material. And in Germany, our way to deal with that is we work with Arrhenius. We know there are uncertainties and argue by applying margins. We deal with authority, or especially in Germany, is with the TÜV, from the authority ordered technical experts. This made it practical and works. And one feature to be mentioned is that also we do not only calculate the residual lifetime, we also calculate a reserve you have. So you can be in a limit. For example, your equipment was initially qualified, and you see by the low temperature at the location, the qualification is fulfilled for 40 years, for example. But we also can check what happened after 41 years. Did we get a red lamp or not? Yeah, and this shall give the feeling about are we near the border, or is there a lot of reserve? And if a lot of reserve is, it's a good argumentation against authorities in the process of licensing. Yeah. So the same for radiation. Because of the time, I go not in detail. It's the same, but the formula is different, as you can imagine as experts. It's a power law. We are using considering dose rate effects. So we also have a possibility to treat other aging mechanisms, not only the thermal and radiological ones, also water treating in case of moisture and electrical fields simultaneously, for example. This all is based on experiences, and this software of concern is able to give a hint. Be careful here. You have to check this not to have any problems with water treating. This is serious. It makes pang. It's not recommended to run to failure. Okay, there's a program. COMSY program is able to contain all maintenance activities or other researches you want to connect to the special cable type. You can upload that, and you will have it available after clicking on a certain cable. So this is what we call this is a component management system. And the last, I think this is the last point I will highlight, then I come to end, is very important, the trending. The cables are being measured yearly, for example, or each 5 years. It depends on application and who is performing that. And it's quite meaningful to compare the values from the last measurement to the current ones, and you can generate a trend to see is there a trend or not. In best case, it's not. So it's randomly, but if you have a trend, you have enough time as operator, maybe 5 years, to find a solution for this problem. Yes, and the reporting, one sentence to this, you need for your authorities an evidence for your components, and the best way to do that is to have a print of all relevant data. You should avoid giving software because of questions about software qualification. You cannot answer that. Easiest way is have a print, all data, and with a small calculator on hand, authorities can check if the calculations are correct or not. Okay, time's out, I think. Yeah, okay. Yes, I come to the end now. Do you have any questions?
Well, thank you, Sascha, for this insight in the COMSY tool. And if there's any question from the audience.
I understand that you use the RNA flow to predict the residual lifetime. Is it possible to follow any statistical information concerning failure rate of cable system in particular?
Yes.
Room of your
Sure.
Or not possible? Or?
Sure. In particular for the INC equipment, we are doing that.
Okay.
As you have electronics, you cannot go in detail, work with Arrhenius law for each part of the electronic unit. So in this case, we only work with failure rates. And if we have a failure rate from experiences, we have in our device library available.
But it's not applied for cable system.
No,
accessories?
no, we are not. It's not because there are no data available as far as I know, because it's very seldom you have a failure on the cable. It's not the point. It's different to electronics. You have one.
Is there any other question? Just a very brief one. Which measurements are you using in your database?
We are using the temperature measurements. We are using the activation energies. We take from the literature, or we determined by ourselves by labs. Elongation at break tests, for example, is the method we are preferring. Mm-hmm. The electrical parameter are also possible, mm-hmm. But the mechanical value comes before the electrical loss of electrical strength. So what we try here is to be conservative.